Well, greetings, Mr. Kolazar's class. Today we're going to start out in chapters 7 and 8 from in the textbook. So we're going to combine the next two chapters together, looking at ionic and covalent and metallic bonding and naming. So we're going to put the next two chapters together and kind of break it up into a couple different sections. So in the textbook, chapter 7 and 8 is where we're going to be heading. Good news, at the end of each section, I'm going to try to include a new chemistry joke, just to add a little bit of entertainment to each section. So we're going to look through why our atoms are going to make chemical bonds, describe the formation of positive and negative ions by their electron configuration, and the formation of ionic compounds is what we're going to be focusing on today. So first off, a chemical bond is going to be a force of attraction that holds atoms together as a functional unit. So a chemical bond is going to form between two atoms or more to make a compound. Key part is also only our valence electrons are going to be used. They're the ones that are in the outermost energy level. So those are the ones that are going to be our bonding electrons. Those valence or outer electrons. Now, scientists found out, don't worry about writing this first part down. We're going to write this part in just a second. But the Octet Rule. An observation that when the s and p orbitals are completely filled, so 2 in the s, 6 in the p orbital for any energy level, that's a total of 8 electrons, 8 is great. When they get to that 8 electrons, that's what the atoms want to do. So the Octet Rule is the idea that atoms want to gain, lose, or share electrons to get to that number of 8. So to require a full valence of 8. Ones that don't, hydrogen through boron elements 1 through 5 only want 2 electrons, so instead of the octet, they're the duet rule. So to do this, ions want to be formed, charged atoms due to unequal sharing of protons and electrons. So they do this to achieve a full valence shell. They're more stable forming these compounds. To get to that 8 or full valence. So we're going to form compounds being more stable that way is the reason that these compounds are formed. The first type, positive ion. Ions that are going to be formed when an atom loses one or more valence electrons. Now we call these cat ions. Cat ions are the positively charged particles. Now to remember this, cats have pos. Cat ions are positive in charge. So cat ions are going to be cat, the positive formed. Example would be sodium losing an electron would become a positive charge, and an extra electron would have been lost or donated away. So sodium would give up an electron to become a cat ion, are positively charged ions. So we'll first off, isoelectronic we'll look at first. Now we'll look at that second. So let's look at a few elements first. Our first one, we've got sodium, Na, magnesium, Mg, aluminum, Al. And we've got each of those electronic configurations, 1s2, 2s2, 2p6, 3s1. Now if we notice 2, 6, there's our 8 outer electrons. If we're able to lose 1 electron, we can get to that full outer energy level. Sodium is going to want to lose that 1 electron. As it loses 1 electron, we have that 2s2, 2p6 is the electron outer configuration. So it's stable at that time. So if it loses 1 electron, the overall charge of sodium is a +1. How we're going to write that out, ion symbol is Na with a plus charge. You can write 1 if you would like to, but we don't need to. We apply that it's 1. And if you want to write the 1, you can. Don't need to write the 1. It's implied that it is there. Magnesium, 1s2, 2s2, 2p6, 3s2, we notice the 2s2, 2p6. If sodium was to lose these 2 electrons, it would have that outer valence of 8. So losing 2 electrons, 1 was plus 1, losing 2 plus 2. Now when we write magnesium, it's going to be a plus 2 charge. And finally, aluminum, 1s2, 2s2, 2p6, 3s2, 3p1. We've got our 8 valence there if we're able to lose these 3 electrons. So we'd form a plus 3. So aluminum would be a plus 3 charge. Now these are all superscript, like Superman flying up in the air. The ion number, that plus or minus number that's going to be associated, write that up in the air next to it. That's our way of writing out those. Now all of these elements now, the 1s2, 2s2, 2p6, have our isoelectronic elements that have our ions of the atoms that have the same electronic configuration because they same number of electrons. In this case, this table, all of them, 1s2, 2s2, 2p6, look like neon. So they're all the same isoelectronic. Actually, iso means same electron configuration after they lost those electrons with neon. Just the opposite, ions can gain, or atoms can gain electrons to become ions. If they gain 1 or more electrons, they become a negative ion. So by gaining electrons, they become negative. Electrons have negative charge. Our hint for remembering anions, please write this one down. Anion, way to remember it, a negative ion would come together to make the word anion. So if like element chlorine was to gain an electron, it would have Cl and it would be a negative overall charge, that superscript written up there, saying that chlorine has now gained an electron. So a couple examples here: fluorine, oxygen, and nitrogen. 1s2, 2s2, 2p5. Fluorine is going to want to gain an electron to become 2p6. So we're going to add 1 electron to its outer level. It wants to take 1 electron in order to have a full valence, the 2s2, 2p6. So if it gains, number of electrons gained, 1, charge of this is going to be -1 since electron's negative charge. Fluorine with a negative charge is what we're looking at. We don't need to write the number 1 in, it's applied that it's there. Oxygen, 1s2, 2s2, 2p4. Now to get to the 8 outer electrons, we're at 6 total. What we're going to do is oxygen will need to add 2 more electrons to get to that 8 outer. So gaining 2, -2, oxygen would be a -2 charge. And finally nitrogen, 1s2, 2s2, 2p3, has 5 valence. We want to have it gain 3 electrons to get to 2s2, 2p6. Gaining 3 gives us -3 charge, or nitrogen would be with a -3 charge. Again, all of these now end in 1s2, 2s2, 2p6. All of these also isoelectronic, same electronic configuration as neon. So electronegativity, revisited from last chapter. This was in chapter 6.3. Just to remind ourselves, electronegativity, ability to attract electrons when bonding. So if we were to start out, we have our stair-step line to put in somewhere along that line, and what we're looking at is as we go down, the electronegativity is going to decrease because of our electron shielding. so it's harder to take electrons in. And as we go across, it's going to increase the ability to attract electrons, increases due to our proton pulling power. So make sure we put these notes down on this chart. Now, our ability to attract electrons as we move across increases, and as we go down decreases. So remember, the noble gases don't attract electrons, so no attraction to those ones. So fluorine was the hungriest of our atoms wanting electrons. So as we're going more proton pulling power, these elements are going to want to attract electrons. Elements down the side are going to want to get rid of electrons. So to look at this, electronegativity, our metals are on this side of the chart. These metals are going to want to become positive ions. So in your notes, metals tend to lose ions, become positive. It's easier then for to lose electrons. Group 1 is going to want to lose 1 outer electron. Group 2, 2 outer. Group 13 wants to lose 3 outer electrons. So it's easier then to lose 1, 2, or 3 electrons instead of gaining 5, 6, 7, or 8 electrons. So decreased pulling power allows them to lose those electrons a lot easier. Metals tend to form positive ions. And then just the opposite, nonmetals to the right of the stair-step line, Nm for nonmetals, tend to form negative ions. That proton pulling power wants to pull electrons in, so groups, not 18, but groups 17, 16, and 15 are going to want to gain either 1 electron, 2 electrons, or 3 electrons instead of losing 5, 6, 7 to get to that 8. So as we're going, our nonmetals are going to form negative ions. And just to end our notes today, Chemistry Cat's going to help us out. Chemistry Cat, how do you know the difference between an anion and a cation? Cations are positive. So good old Chemistry Cat helping us out, looking at the idea of cations are positive, meaning that they've lost an electron to become positive in charge. Ha ha ha.